So good. So that's the gist of all this. So again, if it has the units of momentum, takes the place of momentum, and it's a generator of translations, then if it looks like a chicken, acts like a chicken, then it has to be a chicken. So in this case, we can identify K with the momentum operator, where here I'm writing it as P sub X, where X only means that it's the momentum operator in the X direction. Now, for now, since we're only working in one dimension, writing the sub X is not quite necessary. But when we get into multiple dimensions, we will definitely need some sort of subscript on here because we're working in the X direction, Y direction, and then Z direction. So good. So I made a note of this in class, but again, we have the microscopic translations then become, so if I wanted to translate my state from whatever the initial position is to some that position plus A, then this is equal to the limits as n goes to infinity of 1 minus I times the momentum operator divided by h bar times the distance I want to move it, A divided by n, all raised to the nth power. So here I'm just doing it in an infinite number of steps. And then as we've seen this before with the rotation operators, this thing just becomes e to the minus momentum times that distance I want to move it divided by h bar. So good. So next thing we want to look at is, okay, so what overall is the physical significance of this momentum in momentum space, or in quantum mechanics anyways? So to do that, let's look at the time evolution of a particle of some mass m moving in a potential well, which is given by v of x. Okay. So we know classically, this guy's going to be given by the Hamiltonian, where the Hamiltonian is equal to, so remember this is equal to the kinetic energy plus the potential energy. So in this case, kinetic energy is always simply equal to the, mv squared over r, or sorry, 1/2 mv squared over r. That is the centripetal force, never mind. So that's kinetic energy, which is then also equal to what? The momentum squared divided by twice the mass, right? And then v here, v is only a function of position. It's not going to be a function of velocity itself. Have you guys looked at the Hamiltonian before?
I don't think we, my class, I don't think we did a whole lot with it.
Okay.
Yeah, I did.
I know in Clayton's class, we didn't really do much with it all. I think we just kind of talked a little bit about it at the end of the day. But the Hamiltonian is related to the Lagrangian by the partial derivative of the Lagrangian with respect to the velocity times the velocity minus then the Lagrangian. So this is what we call the Hamiltonian. So the Hamiltonian is actually a Legendre transformation from the Lagrangian to the Hamiltonian. So this is actually a Legendre transformation. So if you've taken, especially statistical mechanics, you'll talk a lot about Legendre transformations. That's how you relate entropy to enthalpy to free energy to et cetera, et cetera. So you use all these different partial derivatives related by all these different things. So anyways, so in classical mechanics, this is what we have, right? So the Hamiltonian is simply equal to the momentum squared divided by twice the mass, plus then the potential. Okay. So the question is now, if I want to make this thing quantum mechanical, how do we then make this thing quantum mechanical? Well, turns out to make things quantum mechanical, typically all we're going to do is we're going to let our momentum here go to the momentum operator. So this guy's going to be the momentum operator. Position then is going to go to the position operator. And then finally, we have to insist that the commutation relation between the position and the momentum is then simply equal to IH bar. So this is actually what adds, as we talked about before, the Heisenberg uncertainty principle. So this has to be instilled. And then this is actually what makes things quantum mechanical. So typically quantum mechanics just comes by promoting all of our positions and momentums to operators instead of just regular coordinates. And then we have to insist on the commutation relation to add in the Heisenberg uncertainty principle. And this is basically just what makes things quantum mechanical. So what that means then is that our quantum mechanical Hamiltonian then is going to be equal to the momentum operator squared divided by twice the mass, plus the potential, which is now a function of the position operator instead of just the position. And again, we have to insist on this commutation relation to be true. So this is typically what's just going to make our stuff quantum mechanical. So most of the time, quantum mechanics is typically just classical mechanics, which we make things now operators and then just impose the uncertainty relation. And then that makes it basically quantum mechanical. Not many times can we actually derive something from quantum mechanics. This will happen every once in a while, but typically not so often. Okay. So good. So let's look at two things. So the first thing I want to look at is how does the expectation value of the position evolve with time? Right? So what is the time evolution of this guy? This will help us kind of understand a little bit better of this momentum here and how all this stuff kind of works together. So remember, if I want to know the time evolution of some expectation value, then this is equal to 1 over IH bar times then the expectation value of the Hamiltonian commutated with or commuting with the operator itself A. And this is assuming that the operator A is not time dependent. Okay? Otherwise, if it was time dependent, then we would have some extra term which has to do with the partial derivatives. But remember, this is then our, sorry, we got a negative sign here. There we go. So this is our time evolution of the operator or the expectation value. So here, what we want to know is how does the expectation value of the position evolve with time? So it's going to be equal to I divided by H bar times, then I'm going to get a psi commutation relation between the Hamiltonian and the position, psi. Okay. Because here for us, A is simply equal to X. Good. So let's write this out. So this is equal to I divided by H bar psi. Let's write the Hamiltonian. So this is then px hat squared divided by 2m plus v of x, commutation relation with x, psi. So this guy then is going to be written as I divided by h bar times. So I'm going to get a 1 over 2m times the expectation value of the momentum operator squared, commuting then with the position. Remember, I can break this up into two terms, psi plus the expectation value of the potential, which is only a function of position, commuting then with the position, this guy. Now, my first question then is, what then is the expectation value, or sorry, let me say it differently. What is the commutation relation between the potential, which only depends on position, with the position operator? So this commutation relation here, what should be the value of this commutation relation?
Should it be 0?
It's going to be 0. Good. The reason for that is good. So the reason for that is, I'm going to write it over here, is that, remember, any operator automatically commutes with itself. Right? This guy's going to be equal to 0, which means the potential, right, is going to be some function of the position, which means since it's only a function of the position, so whether this thing is then equal to something like x cubed or anything else, then I'm going to get something like an expectation value of, or at least commutation relation between x cubed and x. But anything with x simply commutes with itself, so this thing is automatically going to be 0. So since this thing is only a function of position, this expectation value will be 0 because the commutation relation of this guy will be equal to 0. So the only non-zero commutation relation we're going to have is this guy. So good. So let's keep working on it. So then our time evolution then of the position is then, or the expectation value of the position, then is going to be I divided by h bar 1 over 2m times psi. Now remember, if I have an operator squared, so let me write this over here. So if I have a times b commuting with c, then we can rewrite this then as a times the commutation relation between b and c plus commutation relation between a and c times b. Right? So this was one of our identities that we wrote down before. Would you stop doing it? Good. so this is then going to be, so let's put this in. So this is going to be the momentum times the commutation relation between the momentum and the position. Let me put a bracket here. Psi plus psi, commutation relation between the momentum and the position. Would you stop that? Seriously. Times the momentum, all times psi brackets, right? Good. So now I actually wanted to go back. So here, but remember that the commutation relation between the position and the momentum is IH bar, which means that the commutation relation between the momentum and the position is going to be negative IH bar, right? It's just going to be opposite of this because we're just doing it in opposite order. So using the fact that PXX is equal to minus IH bar. So this term here is going to be simply minus IH bar. This term is also going to be minus IH bar. They're both simply constants. So I'm going to factor those out. So this is minus IH bar. This is also minus IH bar. So this H bar and this H bar cancel with this one. This negative I and this negative I make this one positive. So this guy is going to be equal to 1 over 2m times then what? The expectation value of the momentum plus the expectation value of the momentum. But since these two are the same, then that's twice, so that gets rid of this guy. So this guy is simply equal to then the expectation value of the momentum divided by the mass. That's doing okay? So what this thing says then is that what? The time evolution of the position, or the expectation value of the position, then is equal to the expectation value of the momentum divided by the mass, right? But what does this mean? So the expectation value, so the time rate of change of the expectation value of the position basically is the same thing as the velocity. So what this is saying is that the velocity then is equal to the momentum divided by the mass. But remember that momentum, what's momentum equal to?
V.
mv, so this is the mass times the velocity. So this thing is simply saying that the velocity is equal to the velocity, right? So this is the same expectation value that we would have in classical mechanics. So basically all this thing is saying is that what? How this thing actually evolves with time, the position acts just like the velocity, which means that the position dot is then equal to the velocity, right? So what this thing saying means then is that the time evolution of the expectation operator, or sorry, of the expectation value of the position acts exactly like it does in classical mechanics. So the average of the position then evolves with time exactly the way that it does in classical mechanics. So this is exactly the same as classical mechanics. Now, let me ask you a question. So just because the expectation value or the average value of the position evolves in time, just like classical mechanics does, so just like the velocity, does that mean a single particle will evolve this way?
No.
No, absolutely not. That's right. So basically, each particle is going to kind of do what the hell each particle wants to do, but a collection ensemble of them together will evolve in time just like that of classical mechanics. Typically, this is what's known as the Aaronfest Theorem. How do you spell Aaronfest? There it is. So Aaronfest Theorem. So the Aaronfest Theorem basically says that what? Each individual particle will not evolve in time as classical mechanics does, but an ensemble of particles will have an expectation value which does evolve classically according to classical mechanics. Now, another way we can see this is we can look at the time rate of change of the momentum. So if I look at the time rate of change of the expectation value of the momentum, then this guy then is equal to, again, I divided by h bar, expectation value of the Hamiltonian, times then the momentum operator, or expectation value of this guy. So we don't know how to handle this yet. we'll talk about this in a little bit, but it turns out that this is equal to then the expectation value of minus the derivative of the potential with respect to position. Now, classically, what's p dot? So what is the time derivative of the momentum? You guys remember that from classical mechanics? So what's p dot? What's the time rate of change of the momentum?
Force.
Force, good. So this says that the force on the left-hand side, and what is minus the derivative of the potential with respect to position? That is also force, right? So basically, again, even the momentum operator or the expectation value of the momentum also evolves with time exactly the same way that it does classically. Just says that the force, again, is equal to the force. Again, each individual particle does not have to abide by this, but again, an ensemble of particles do have to abide by this. So again, this is just an Aaronfest theorem. So a good question then is, when does this actually break down? So when does this not abide by, so when does this kind of break down? When does this not abide by classical mechanics basically anymore? So since this thing is equal to the force, so let's go ahead and call this term the force. So let's look at a Taylor series expansion of the force, right? So if I looked at the force, then this is going to be equal to the force evaluated at the expectation value of the position. And then I get a plus x minus x average, or in this case, the expectation value of the position, times then the derivative of the force with respect to position, evaluated at x is equal to the expectation value, plus 1/2 factorial times x minus the average position squared, times then the second derivative of the force with respect to position, evaluated at x is equal to the average position, plus blah, 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 blah. Now, the first order term here has to be equal to 0. Right? So this term is equal to 0, which means we're left with these terms plus any higher order term. So this is then going to be f delta x plus 1/2 factorial times x minus this guy squared, but this guy minus this guy squared is actually the same thing as the uncertainty. So this is actually the same thing as the uncertainty in the position squared, times then the second derivative of the force respect to position, evaluated at x is equal to the expectation value, plus blah, blah, blah. So basically what this thing says then is what? The force acting on this particle will abide by the classical mechanics, right, for this ensemble, as long as this term here is small. So basically, as long as this term or any other term is small, then this thing is going to abide by classical mechanics. So basically what that means then is that what? For this thing to be small, what has to be true then is that what? The uncertainty must be small compared to then the derivative of the force. This must be true. Or just that this term must be much, much less than this term. So a different way I can write that is that the uncertainty then must be much, much less than the force. So anytime that the uncertainty in the position of this object is much, much less than the force which is actually acting on the object, then this thing is going to abide by classical mechanics. Now, this is true whether the thing is a macroscopic object or a microscopic object. So this relationship is true for any object. Again, as long as this uncertainty here is much, much less than the force itself, then this thing is going to abide by this term be going to 0, which means the force then is equal to the force along the expectation value. So as long as that is true, then the rest is true. Now, this happens, of course, when the uncertainty of the position times the uncertainty in the momentum is much, much greater than or equal to h bar divided by 2, i.e. the Heisenberg uncertainty principle. So as long as the uncertainty of the position times the uncertainty in the momentum is greater than or equal to, getting so many emails today, the momentum, then this is going to hold, right? So in this case, the Aaronfest theorem will hold so that the force will be the force, and that this thing is going to move along, again, for the ensemble, has to move along some sort of classical trajectory. Guys, okay? You're always a pillar of certainty there, William.
All right.
All right, so good. So the next thing we want to know is, okay, so what does the translation operator look like in position space? And then from there, we'll gain information about the, what's the word I'm looking for? Momentum operator as well. So remember we talked about before is that this guy here is what? Hermitian, which means that our momentum operator is also Hermitian. So this guy's also Hermitian. So many emails. Okay. So good. So let's consider then, so from here to determine what this thing looks like in position space, we're going to consider then a macroscopic displacement being replaced by an infinitesimal displacement. Okay, so let's say we have some small infinitesimal displacement, delta x, where delta x is much, much less than x. Okay. So to determine how the translation operator then looks like and acts in position space, let's act this guy then onto some state psi. Right? Now, again, we know how this guy actually acts onto a position ket. So let's do an expansion of this in terms of the position basis, right? Let me write it out in full glory detail. So don't really miss what's going on here. So basically all I'm going to do is I'm going to insert an identity here. Right, so here's my identity. So I'm going to write this as my translation operator, delta x integral dx of then x psi, right? So just using my completion or identity here and then expanding this guy. Now, since the momentum operator here only depends on delta x, not on x, then this can come inside of the integral. So this is going to become equal to the integral of dx of then t delta x acting onto x psi. Okay. Now this guy acting onto him, we know that he's going to translate him to the right by an amount of delta x. So this is going to be equal to the integral of dx. And then I get an x plus delta x psi. Okay. Now from here, though, we want to transfer this delta x now onto this one so we can see what actually happens to the wave function itself. So let's define a new parameter x prime, which is equal to x plus delta x, which means dx prime is then simply equal to dx. So that x is equal to x prime minus delta x. So this is going to become equal to the integral of dx prime, x prime minus delta x psi. Okay. Behind that thing for now. And then this is equal to the integral of dx prime, x prime, and now I have psi of x prime minus delta x, right? So this is our wave function. Now, to make a little more sense about this, since delta x here is much, much less than x, or x prime for that matter, what we can do then is we can do a Taylor series expansion of the wave function itself. So let's go ahead and do a Taylor series expansion. So since delta x is much, much less than x prime, then let's Taylor expand. There we go. About x prime. Okay. So what do I mean by that? So what I mean is that t delta x, which again is equal to the integral dx prime of x prime delta, I'm sorry, there should be a psi, equals, psi, there we go, x prime minus delta x. Good. So let's do a Taylor series expansion of this guy. So this is going to be equal to then the integral dx prime times x prime times. So if I do a Taylor series expansion, I'm simply going to evaluate psi here at x prime. So this is going to be psi of x prime. And then from here, we get a subtraction of then delta x, and then the first derivative, or in this case, partial derivative, there we go, of psi with respect to x prime. And this guy is evaluated at x prime. Okay. Guys doing okay? So this is then equal to the integral dx prime. Let's see, do I keep it this way? Yeah, I'll keep it this way. Okay, so now this has a psi here. This also has a psi here. So let's go ahead and factor out the psi. So I'm just going to rewrite this guy. So I'm going to write this as then x prime. So let's write it this way. So this is now going to be the inner product between x prime and psi. And then this guy is going to be a minus delta x. And then I'm going to get a x prime partial. Let's see, now let's write it the other way. Yeah, I'll write it this way. So delta x, and then I get a partial with respect to x prime, then x prime psi. So let's write it this way. Now, I have a psi here, I have a psi here, so I can actually factor that guy out. And let's rewrite this then as, so how do I want to write this guy? Yeah, so let's rewrite this then as, so let's do it this way. So this is equal to the integral dx of x prime psi minus delta x integral dx prime, and then I get an x prime, and then I get a partial of x with respect to x prime, and then I get a, what, x prime psi. Okay. Now, again, this thing here is simply the identity, so I'm going to factor that guy out and pull this guy to the right. So I'm going to rewrite this then as what? 1 minus delta x, and then I'm going to get the integral dx prime, x prime, partial x prime, all acting on psi. You guys doing okay? You understand what I did?
Yeah, I think so.
Okay. Now, we also know that this guy acting onto psi, oops, I forgot my psi on the side. I may be being a bad teacher. Okay, so this is t delta x acting on psi. Good, okay. Now we also know this guy acting onto him with a small delta x is simultaneously, so let's write it on this side, 1 minus I px divided by h bar times delta x all times psi, right? So this was from when we were down for the momentum the spatial translation operator before, and then this is the psi. Right. Guys doing okay? So basically, now if I match the left-hand side to the right-hand side, so the sides are the same here, the 1 is the same here. So basically what this means then is that what? Anything that shows up in front of or behind the delta x must be the same thing. So what this implies to us then is that what? I divided by h bar times the momentum operator then must be equal to this stuff here, right? So this has to be equal to the integral of dx prime of then x prime delta x prime x prime. That's doing okay. Now, to make more sense out of this, let's determine its matrix element. So let's look at the matrix element. So for the matrix element, let's take the x, p of x with psi. Okay. So according to what we have here, this is then going to be what? H bar divided by I. And then I'm going to get an x integral dx prime x prime partial x prime psi. Right? Okay. Now, since this only depends on x and x prime, I can pull this guy inside of the integral. So this is going to become minus I h bar integral dx prime times the inner product between x with x prime times the partial with respect to x prime of then, write it this way, simply psi of x prime. Now, what's the inner product between x with x prime? Direct delta function. So it's going to be a dx prime delta x minus x prime partial with respect to x prime of then psi x prime. But when we do the integral over x prime, all that's going to do is force all the x primes to then be x's. So finally, this is going to be equal to minus I h bar partial of psi of x with respect to x. Okay. Now, before we talk about what all this means, let's do one more thing. Let's let psi go to x. Okay, which basically means that what we want to know, what is the expectation value then of the momentum? Okay. So let's look at that guy. Actually, let's call it x prime. So if I do x, px, x prime, and then we'll do one more thing after that. And actually, we'll look at the expectation value after this. So if I let psi go to him, I was thinking about the other way. So, well, that's fine. We'll work with this. So this is going to be minus I h bar. And then, so this is going to give me a what? So let's go back to here. So let's go back to what I had written here. So I'm going to have an x here, integral dx prime. And then I get an x prime. And then I get a partial x prime. And then I get an x prime with x prime. That doesn't make any sense at all. That makes sense. Oh, ignore this one. Sorry. Let's do it differently. I don't think about that one. That doesn't make much sense. So let's do this one. Let's change this to a psi. So let's instead look at the expectation value, psi, momentum, psi. So let's look at the expectation value. Okay, let's do it that way. That'll make a little more sense. So good. So if I do that, then in this case, let's write this again. So minus I h bar, and then I got a psi integral dx prime, x prime, partial x prime, psi, right? Bring psi on the inside, and then this is equal to minus I h bar integral dx prime of then psi x prime, partial x prime, x prime psi. But remember, this is the wave function, so this is the star of the wave function. So finally, from here, what we get is that the expectation value of the momentum, oops, in position space, then is equal to minus I h bar integral dx prime of then psi star x prime partial x prime psi x prime. Okay. And this is all equal to the expectation value of the momentum. So what does all this stuff mean? Now that I spent way too much time actually acting on this. So basically, if I put this guy here, mix that together with this guy here, and the expectation value, what all three of these different things seem to point out to us is that, at least in position space, my momentum operator in position space, so in x space, then is given by the representation of minus IH bar times the partial with respect to x. So that's what all this stuff actually is pointing to. So all this means that is, again, in position space, my momentum operator acts as the partial derivative of all of this stuff. So again, this is something that you should be familiar with modern physics. So in modern physics, you just put that guy in there and said, this is what it looks like. So that way, when you calculated the expectation value of the momentum, you automatically arrived at this guy because you said the momentum was equal to minus IH bar partial with respect to x. But again, all of this basically together insists that it actually looks this way. So this is actually where it comes from. So it comes from just looking at the time evolution operator, or sorry, the position operator, the translation operator. Man, I can't talk today. So looking at the translation operator and seeing how that thing actually acts then on the wave function. What happens then if I apply this guy n number of times? Well, in this case, we would then have x with px raised to the nth power of psi, which basically means I just get n number of copies of this. So this is going to be equal to minus IH bar raised to the nth power times then the partial, the nth partial with respect to x, acting then on the wave function x psi. So good. So if I act this guy n number of times, then I simply square or do n powers of this guy. So for example, when you're looking at the Hamiltonian and you're looking at px squared, well, all that means then is in position space. And then this guy is simply equal to minus IH bar quantity squared times the second partial derivative, which is then equal to minus h bar squared times the second partial derivative. So that's all this thing means. So if I act on it n number of times, then I get n copies of the same thing, all acting then onto this second wave function. But again, this is all stuff that you should have seen before from modern physics. But again, this is actually where it comes from. Modern physics. Any of this ringing a bell for modern physics? Kind of, sort of.
Yeah.
Well, who did you have for modern physics?
Purcell.
Purcell, okay. And Clayton, who'd you have for modern physics?
Purcell.
Purcell, okay. Very nice. So yeah, so I know he goes over those things. I don't know why that's it. All right, so good. So the next thing we're going to start looking at is momentum space. So we've seen position space. So basically now what we want to do is generalize all of this to now momentum space. So momentum space, we want to basically do the same thing. So to go from position space to momentum space, I'm simply going to replace the position kets now with momentum kets. Okay. Where in position space, if I took the position operator and I acted that onto the position kets, then this just returned back the position. Well, in momentum space, it's going to do the same thing. So now, why did you go to yellow? Anyway, that's fine. So now if I act the momentum operator onto the momentum basis, then this is going to return back the momentum times the momentum basis, right? So the momentum basis here is an eigenstate of the momentum operator. So good. So further, we also saw that what if I took the inner product between x with x prime, this then gave me delta x minus x prime. Because position space is continuous, well, since momentum space is also continuous, what that means then is the inner product between the momentum and momentum prime, this is also then equal to p minus p prime delta, right? So also equal to our direct delta function. And since the inner product of the state psi with itself must be equal to 1, we can now expand this guy in terms of the momentum basis instead. So we're going to put in our identity right in here. So it's going to be equal to the integral over the momentum of psi, momentum psi, which is simply equal to what? The integral of the momentum times the inner product between the momentum and psi modulus squared. So this term here, everything without the integral sign, then this is equal to what? The probability of finding the state with momentum between P and P plus dP, right? So all that's what this thing means. So here again, so dP times the modulus squared of the inner product between P with psi, then is simply equal to the probability of finding the particle with the momentum between P and P plus dP, which means by integrating over the entire space, this thing has to have a probability of 1. Okay. We also have that the inner product between momentum and psi is then equal to the momentum wave function. So we're going to define it this way. So psi of P. So this is what's known as the momentum space wave function. So just the equivalent of X with P. So again, all this means is that this is the state projected onto the momentum basis. Right? So if this is my state psi, and then this is my momentum basis P, then this is then the inner product between the two, which then is the projection of the state onto the momentum basis. So this is then P psi. Okay, all this means is we're projecting our spin state onto the momentum basis. Or more in general, not just our spin state, but our quantum state onto the momentum basis. So the next thing we want to talk about is how are these two spaces related to each other? So how is momentum space, related to position space? So what's the connection between these two guys? Okay. So basically to do that, we're going to use what we just came up with. So basically this stuff here. So basically I'm going to use this expression here, but I'm going to replace this psi here with the position basis. Okay, and then I'm just going to simply use the result. So all I'm going to say here is then that the matrix element of X momentum operator P, right? So this guy then is what? This is our matrix element. So we have two options. Remember that our operator can either act to the right, which means if it acts to the right, in this case, I'm going to act the momentum operator then onto the momentum basis. This guy just pulls out what the momentum happens to be. So this is going to be written as the momentum times then the inner product between the position basis and the momentum basis. Or we can act in the opposite direction. I can act then my momentum operator onto my position basis. And if I act on it this way, then this thing is also then equal to, well, we know this guy acting on him in position basis is minus IH bar times the partial derivative. So it's going to be equal to minus IH bar, partial derivative with respect to X of the inner product between the position basis and the momentum basis. Guys doing okay? So putting these two things together, what I get in this case then is that the momentum times the inner product between the position and momentum then must be equal to minus IH bar, partial derivative with respect to position, times the inner product between the position and momentum. But also remember that the inner product between two bases is what? This is also the transformation matrix to go from one to the other one. So notice also that the inner product between P and X is then the transformation matrix going from momentum space to position space. So here we're going from P to X. So remember, we always go to from. Wait, is that right? No, from to. Yeah, there we go. So from and to. So remember, the inner product then is to and from. So here we're going from momentum space into position space. Good. So what this does is it actually gives us a first order differential equation that we can solve then for this matrix elements for our transformation matrix going from one space to another space. So let's go ahead and do that. So here I'm going to write this now as a full derivative. So this is going to become, so let's use separation of variables. I'm going to put this term over here, the other term to the other side. So here I'm going to get a what? So I'm going to get a minus I. So this is going to become an I divided by h bar times p times dx. That must be equal to d xp divided by inner product between x and p. Now for this guy, I'm going to integrate both sides. So the right-hand side, this thing is simply a natural log. So I'm going to get a natural log of the inner product between x and p. The right-hand side, when we do this integral, we do it much like we do in statistical mechanics, where we're going to pretend that the momentum and the position are separate variables. So here, to do this integral, put an asterisk on here. So we will hold, or let's do it this way. So let's write it. So here, p and x are independent. And when we do the integral, we're going to hold p constant. Okay, so we're basically going to say that we're going to integrate this at a constant momentum, which means the left-hand side then is going to become I times px all divided by h bar. So since I want the matrix element to go from momentum space into then position space, we then have to take an exponential. So finally, what we get then is the relationship between the position space and the momentum space via our transformation matrix is going to be some n value, right? E to the I momentum times position divided by h bar. Oops. Not a momentum operator, it's just momentum. There we go. Guys doing okay? Yeah. Good. So, and here is just some normalization constants. We actually have to determine what that normalization constant is going to be. So, let's determine a normalization constant. So to do this, first thing to note is that what? The inner product between x and x prime, as we talked about before, is equal to the direct delta function of x minus x prime. But notice that we can also put in an expansion over the momentum operators here. Right? So I'm going to put an identity here. So I'm also going to write this as the integral of then dp of then x p x prime. Now, if I use this guy here, then this is going to be equal to then what? An n squared. So I'm going to write this as a modulus n squared because n can in general be what? Complex. So this inner product here is going to give me an IP x. Right? Actually, I don't need that x there either. So ignore that x there. Sorry about that. It should just be p. So this is going to be the integral of dp of e to the I px divided by h bar. This term here then is going to be the complex conjugate of this since it's in the opposite order, and it's also going to be evaluated at x prime. So it's going to be times minus I px prime divided by h bar. So this guy then is going to be equal to n squared integral dp of then what? E to the I p x minus x prime all divided by h bar. Guys doing okay? if I integrate the right-hand side, we've seen this before, this thing actually acts like a direct delta function. So what's going to happen is that this thing acts as a delta function, has the greatest contribution when x minus x prime basically goes to 0. Right? So this thing is going to be equal to, with a normalization constant, which is 2 pi times h bar, that's n squared times delta x minus x prime. So the value of this integral is simply a direct delta function with this factor of 2 pi with the h bar. H bar comes from this h bar down here, but the 2 pi comes from the normalization. So since I have a direct delta on one side, direct delta on the other side, those two things have to cancel. So what that means is all this stuff here has to be equal to 1, which means that n then must be equal to 1 over the square root of 2 pi h bar. So this is my normalization constant n. So putting that back in here, what this means then is that my matrix element for my transformation matrix to go from momentum space to position space then is equal to 1 over the square root of 2 pi h bar e to the I momentum times position divided by h bar. Okay. Now again, we just have to remember that when we're doing this integral, or whenever we use this, we're holding one of these two guys constant. So if I'm integrating over the momentum, you're holding position constant while you're integrating over the momentum, or if you're integrating over position, you're then holding momentum constant while you're integrating over the position. Okay. So whatever it is that you're integrating over, the other one is held fixed. So I'll put that asterisk over here. So whatever you're integrating over, over, again, whether that's p or x, the other is held fixed. So in that case, that's going to be x or p, depending on which one I'm integrating over. Okay. You guys doing okay? Now, one interesting consequence of this is notice that if my phase changes by 2 pi, right? So basically, if we go from what? So if we change this guy by a wavelength, so if I was looking at, I'm going to ignore the prefactor, but if I look at e to the I, px plus the wavelength, right, divided by h bar, well, this guy must then be equal to e to the I p times x plus 2 pi divided by the h bar. So basically, if my phase changes by 2 pi, then I have to have moved my wave by a factor of the wavelength. So basically, what this means then is that what? P times lambda must then be equal to, or divided by h bar, equal to 2 pi. Which means then that's what? The momentum then must be equal to, let me do it this way, the wavelength. So this basically tells me then that the wavelength must then be equal to h, the h bar? No, just h divided by p, right? Because remember that h bar is equal to h divided by 2 pi. So basically, I'm just taking out the 2 pi from there. So do you guys remember this thing? Or another way I might have seen E then is equal to h divided by lambda. Guys seen this before? Modern physics?
Yeah, I seem to remember that, Professor.
Nice. This is what's known as the de Broglie wavelength. So a natural consequence of this is actually, again, that if I change my system by a factor of 2 pi, then what has to be true is that the wave itself has to move by a factor of the wavelength. So comparing these two sides, sending them equal to each other, basically gives me my de Broglie wavelength. So de Broglie wavelength kind of naturally pops out of my system here. And the last thing, dealing with all this stuff here, not the last thing for today, the last thing is, so let's start off with x and p. So let's say I have x psi. So this is my wave function. So this is equal to my wave function in position space. And then I have my wave function in momentum space is equal to p psi. So last thing we want to know is how then is my position or my wave function in position space related to my wave function in momentum space? Well, if I start off with the top one, then I'm going to expand this guy with again, put in an identity for my momentum operator here. So this guy's going to be equal to the integral of dp of then x p psi. This guy is just him, right? The momentum wave function. This guy is this guy. So this is then equal to what? 1 over the square root of 2 pi h bar, our normalization constant, integral over the momentum of e to the I px divided by h bar times psi of p. This guy, I'm now going to put in an identity for the position basis. So this is now equal to the integral of dx p x psi. This is equal to 1 over the square root of 2 pi h bar, integral over the position. But this guy here is the complex conjugate of this guy. So this is going to be equal to e to the minus I px divided by h bar psi of x. So this is the relationship between the two. Have you seen these things before?
It's kind of like Schrodinger's equation.
Kind of. I mean, this is what we call Fourier transformations, right? So these are our Fourier transformations that we talked about in math phys. So basically, all this says then is what? If I start off in momentum space and I want to go to position space, then I just have to take the Fourier transform of my wave function in momentum space to bring it into then position space while integrating over the momentum.
Allahu Akbar. Allahu Akbar.
Okay, sorry about that. And then this one says that if we start off with our wave function in position space, then we can go to momentum space by integrating the inverse Fourier transform integrated over the position to then bring it into momentum space. So again, these are the Fourier transforms. The interesting thing here is that it seems like quantum mechanics actually already knows about the Fourier transforms. We didn't have to put these in by hand, right? Not like you would do in modern physics where you'd say, okay, the way I transform from one to the other is using Fourier transforms. Here, we didn't actually put that in by hand. This was automatically given to us by quantum mechanics itself. So inside of quantum mechanics is Fourier transforms already built into quantum mechanics. So quantum mechanics already knows about these Fourier transforms. We don't have to do it ourselves. So, you guys doing okay? Sorry about the event going off there for you. You guys okay?
I think so far.
All right. And how are you doing, Clayton?
I've managed to stay awake, so.
Well, I'm glad I could be helpful for something. Did you work all night last night?
I was off last night, but it was my first night off since
oh, gotcha.
nights.
Gotcha. And did you sleep for like 18 hours?
I managed to get about 4 hours of sleep. I go back to sleep after this, so.
Gotcha. All right. So one consequence of the Fourier transform we'll talk about here, which relates to the next topic we're going to talk about, is because of the Fourier transform, what this basically does is, what this says is, if I look at the second one here, if I have a state which is well localized in position, by doing the Fourier transform causes the state to become unlocalized in momentum. So this is one kind of consequence of this. Vice versa, if I have a state which is well localized in momentum, it also becomes delocalized in position. Okay? So basically the reason for that is, as a property of the Fourier transform, let's say I start off with a system here that is pretty well spiked at a particular location. Right? So if I have this guy, and let's say this is my x-axis and this is some position A, if this thing is pretty well localized at some position A, when I do my Fourier transform to go into momentum space, what happens then is, in momentum space, this thing gets massively smeared out. So what'll happen in this case then is I'll have something that kind of looks more like this, where the corresponding momentum, let's say, and this is PA just for funsies, this thing is not localized in momentum at all. Okay. Vice versa, again, if we did the same thing, so if I started off with something which was well localized in momentum, so that this thing was, again, say something like this, where this thing had a well-defined momentum, again, my Fourier transform going into position space says that this thing is going to nowhere near be localized in position space. So if this is X, and this again is A, again, this thing is going to be spread out, meaning it's not going to be localized in position at all. Okay? This is one consequence of a Fourier transform. Other consequences of Fourier transforms is if I took something which was, say, square. So if I had something that was well localized but happened to be a rectangle at some position A, when I Fourier transform this then into momentum space, what happened in this case is I actually get ringing. So in momentum space, if this was, say, PA, again, this thing is going to become much more spread out, but we also get, actually becomes much more curved too, and we actually get this ringing. So what'll happen then is you get these called ringing. So basically you get these non-zero expectation values basically in these locations. Okay? Now, what does that mean? So what that means then is what? Since I end up with a spectrum of momentum going from position space and into momentum space, we can't just think about this as what? We can't just take a state and Fourier transform it into another state because it becomes so unlocalized. We can't really even talk about the identity of that state in the momentum space if I'm going from position space, or in position space if I'm going from momentum space. So again, the more localized that this happens to be in one space, going to the other space becomes so delocalized, it doesn't really make sense to talk about the state this way. So typically what we have to do then is we have to think about doing the integral as actually being a summation or superposition over all the different possible momentums, which is what we call a wave packet. So basically, to go from one space to another space, you have to kind of think about this as actually being a superposition over all possible momenta, to then think about this in terms of wave packets as an ensemble of particles as opposed to just a single particle going to a single particle. The other thing we can see is that from here, this is actually a plane wave. So when we go from position space to momentum space, or momentum space to position space, our wave in this case is actually a plane wave. So what we're really doing is we're actually taking the superposition over all possible plane waves to turn this thing actually into a wave packet. So going from a well-localized state and momentum to a position space, we're actually doing a superposition over plane waves to turn it into a wave packet then into position space. So this is what this thing is actually really saying. So this is what we call a wave packet. So again, to go from a localized state in position or momentum, we are superimposing, if I know how to spell, there we go, superimposing a collection of plane waves to create a wave packet in position in momentum or position space. So good. So this is what we're really doing. So again, we're simply saying that if, again, we start off with the wave function of position space, to then go into momentum space, we're now creating a wave packet here as opposed to just a single state. So this is a wave packet with a superposition over momentum spaces, or sorry, momentum bases. So superposition, again, of plane waves. So what? So basically, to see how this works, we're going to work with a particular type of wave packets. And that wave packet we're going to work with is, as I wrote in the beginning, what's known as a Gaussian wave packets. Okay. Gaussian wave packets. So basically, for the next part of this chapter, we're going to be focusing on these Gaussian wave packets. Okay. So we'll pick this up on, what day is that? Thursday, so 2 days from today. And we'll go from there. So we're going to spend a whole bunch of time doing Gaussians. Have you guys done Gaussian integrals before?
Yeah, just those yeah, basic ones. Some of the same type of thing.
Gotcha. Okay. So we'll talk a little bit about Gaussian integrals when we actually get there, and then we'll show you all the different tricks to do all these different things. But yeah, so this is what we're going to focus on next time. So we'll start doing Gaussian wave packets. So basically what we'll do from here is we'll use them in position space, transfer them to momentum space, and then we'll look at the time evolution of these guys as well. So we'll involve these guys actually in time and talk about all that different good stuff and what happens to our states in this case. Okay. So what? So that's what we'll pick up next time. Good. Sorry about my brain dead moments. They happen. So good. So any questions at this stage you guys got for me?
I don't think I had any.
Okay. Oh, good. So I'll remind you guys next time of Gaussian integrals and all that stuff. And like I said, we'll look at the time evolution of a free particle, which starts off in a Gaussian state. And then from there, we'll move into basically properties of solutions of the Schrodinger equation. So basically, we're going to start looking at Schrodinger equation in position space. And then we'll look at scattering and one-dimensional potentials and tunneling and kind of all that good stuff. So that'll be the remainder of this chapter. So basically do all that one-dimensional stuff that you probably did in modern physics. Then when we're done with that, we'll be done in this chapter. And I think the next chapter after that will then be, well, we'll start looking at maybe three-dimensional stuff. I think that's what we do next. Yeah, so basically then we'll take all the stuff and then generalize it into 3 dimensions. So, and that'll get us on our way to looking at the hydrogen atom. So how many weeks do we have left? We have what? Half of this week. And then 2 more weeks before Thanksgiving, or 3 weeks before Thanksgiving?
2 weeks and a Tuesday after this week.
Okay. So that would be, so 3 full weeks then.
Yeah.
Yeah. Because we move that Tuesday to this week, so that'd be right. So we have 3 weeks, and then after Thanksgiving we have what, 1 week, or is it a week?
I don't know. that I couldn't tell you.
Sounds good. I think it's something like that. It's either 1 week or a week and a half. So yeah. So hopefully we get through all this stuff. So it should be good. Hopefully. That should be fine. So basically the plan is to get through at least quantization of the hydrogen atom. So that's where we basically want to get to at the end of the day. So that's our plan.